Very good evening to all my dear lovely students. Welcome back to your own YouTube channel, Shri Chaitanya Educational Institutes. My name is Anirudh, and today we'll be talking about the very important topic for organic chemistry, because all the reactions that you study in the chapter Hydrocarbon, today we are going to study, is going to get repeated in almost every other chapter of class 12th organic. Like in the alkyl halides, when you study elimination reactions, that is already there in the preparation of alkenes and alkynes. When you study dehydration of alcohols in the alcohol chapter, that is already there in the alkenes chapter, as all of you already know about. So this series is about Sankalp 2.0, which is for your RE-NEET, which we have to do the revision for. This series is made. So today, in a very short span of 1 hour, we'll be quickly discussing about the important reactions and topics which are present in the hydrocarbon chapter of class 11th. Let us quickly start. So hydrocarbons, as we know, are of 3 types we have to study. That is alkane, alkene, alkyne. Alkene and alkyne I'll keep together. And if time permits, we'll little bit talk about the benzene and derivatives as well. So we'll call it aromatics. Okay, so let's quickly start. As you know, all these 3 topics will be subdivided into 3 parts, which is methods of preparation, physical properties, and chemical properties. So without any further ado, let's start with the alkanes. When you look at your NCERT of alkanes in the methods of preparation, you will find the following methods. So whenever you are revising a chapter, my humble suggestion to you would be that you try to do the method of preparation from first chapter till the last chapter. Meaning, we'll try to prepare alkane starting from alkane, then alkene, from alkyne, from alkyl halide, from alcohols, and so on. You try to prepare alkane from every other chapter. When you go to alkene, you try to prepare alkene from every other chapter. Okay, so that you can revise all the reactions quickly. You can make a flowchart of it. But in the NCERT, only those methods of preparation will be given to you which are actually used in the industry or in the labs. Because every reaction cannot be called as a preparation method. Some reactions have poor yield and all. So there can be so many reactions where alkane would be formed, but they are not taken as a method of preparation in the NCERT. So quickly following the NCERT, we'll be looking at it. Alkanes, the first method is from the alkenes. To go from alkene to alkane, we all know it's hydrogenation. You can use hydrogenation in the presence of nickel or palladium or platinum. When you use nickel, little higher temperature is required, called as Sabatier-Sanders reaction. Okay, with platinum and palladium, it is much more easier reaction to do. So hydrogen gas adds to alkenes and alkynes in the presence of finely divided catalysts like platinum, palladium. Finely divided because we need more surface area for adsorption of hydrogen. It's a surface catalyzed reaction, so we need finely divided platinum, palladium, nickel to form alkanes. The process is called as hydrogenation. Okay. These metals absorb dihydrogen gas on their surface and activate the hydrogen-hydrogen bond. This is something as an assertion reason. If they ask, you should know about it. Okay. So why is finely divided nickel or platinum is used? Is because they absorb hydrogen on their surface to activate the hydrogen-hydrogen bond. Otherwise, we know HH bond is a very strong bond. So in order to make it reactive, this is what we do. Platinum and palladium catalyze the reaction at room temperature. Okay, as I told you, but nickel require relatively higher temperature with nickel. Okay, this is something. Examples are written here. You can just see them. Okay, alkenes will directly go to alkanes. Alkynes will also directly go to alkanes. You cannot go from alkyne to alkene using hydrogen palladium. To go from alkyne to alkene, if I want to go from, for example, here to here, propyne to propene, if I want to go, then you need to know the special reagents like Lindlar's catalyst. You can use hydrogen in the presence of palladized carbon, okay, in BaSO4 or CaCO3 may be mentioned. So this is Lindlar's catalyst. So just palladium won't work. Palladized charcoal will work here. We'll call it Lindlar's catalyst. There is another method which is Birch reduction, where you can use sodium in the presence of liquid ammonia. Sodium/liquid ammonia. all of you know this reaction as well, right? So this will become a preparation of alkene from alkyne. Going from after this, we have from alkyl halide. When we want to go from alkyl halide to alkane, what are the options you have? You have three options, okay? One option is you can directly reduce the alkyl halide, remove the halogen and put a hydrogen there. That is going to be called as reduction. For reduction, there are different reducing agents, but the one which NCERT mentions, which we have to remember, is zinc in the presence of dilute HCl. Zinc plus dilute HCl will provide two nascent hydrogen. Okay, will provide two nascent hydrogen. They are showing it as H2. H2 gas actually is not released here. Two nascent hydrogen will break this bond. One hydrogen atom will go with the chlorine. One hydrogen atom will go with the CH3. So we'll get a CH4 plus HCl like that. Okay. So this is one method. Make sure that you don't use any aryl halide here. Otherwise reaction won't happen. So with the chlorobenzene, because we know there is a partial double bond character here, zinc plus HCl will not do any reaction. Okay, will not do any reaction. Important point, in the previous years also these type of questions have been asked. Okay, so aryl halides will not react because there is a partial double bond character. Their reduction requires very strong reducing agents. With zinc plus HCl it can't happen. Okay, but for the alkyl halides it can easily happen. So wherever you find chloroethane, you can go to ethane from here. Just cut the bond, put one nascent hydrogen here, one here. Propyl chloride to propane and so on. This is the first method. You can also use LiAlH4 here if you want. As you go to alkyl halide chapter, there you will see nucleophilic substitution using LiAlH4. In that case also, a hydride nucleophile comes and displaces the Cl minus leaving group. So again, it will give you the same product, right? So LiAlH4 or zinc HCl is the first option here. Second option is if you want to prepare symmetrical even number carbon alkanes with double the number of carbons. In that case, what you use is a very important named reaction, which is Wurtz reaction. Okay, alkyl halides on treatment with sodium in the presence of dry ether. Sodium in the presence of dry ether, free from moisture, because we know sodium is highly explosive in moisture. So there should not be presence of any water vapor here or any moisture here. Otherwise, sodium will burst. So that's the thing. Solution, it gives you higher alkanes. Okay, doubling up the coupling reaction using sodium. You can couple up monoalkyl halides to alkane using Wurtz reaction. If you have dihalides, if you have geminal dihalides, you can couple them as well using zinc. Then alkenes will form. And you can couple trihalides also using silver, then alkynes will form. So all the three coupling reaction I'll just show you here itself. Okay, I'll just show you here itself. If you have a monohalide, you couple it with sodium. 2 moles of sodium you take, 2 times NaCl will come out, as all of you know, and you get your butane. Okay, this is Wurtz reaction in the presence of dry ether. If you have a geminal dihalide, something like this, you can couple this up as well. You need to use zinc here. You take 2 moles of zinc, 2 moles of this compound, and you can do the coupling in the presence of alcohol. Okay. Then in that case, ZnCl2 will come out 2 times, giving you a alkene. Both cis and trans can form here. Okay, there is nothing about stereochemistry here. Both cis and trans will form, plus 2 ZnCl2. Okay. And if you want to couple up a trihalide, for example, if I take a trichloroethane, okay, you can couple it with silver powder. So heat it with silver powder, and 6 moles of silver you can take, 2 moles of this, 6 AgCl will come out, giving you a but2-ine. Okay, so 3 coupling reactions I have shown you here. Remember them. By coupling you can go to alkanes also, alkenes also, alkynes also. If you couple monohalide, alkane, dihalide, alkene, trihalide, you can go to alkyne. Okay, mechanism of Wurtz reaction is not given in the NCERT, so we'll not have to worry much about it. It's a free radical mechanism. Okay, it's a free radical mechanism, but nothing difficult is asked in the NEET level, so we can skip the mechanism part of Wurtz reaction. Okay, this reaction is called as Wurtz reaction. It is used for the preparation of higher alkanes containing even number of carbons atoms. Okay, after this, the NCERT writes, why can't we prepare propane from here? So the reason would be, if you want to prepare propane, for example, propane carries 3 carbon. So you need to start with a 2 carbon compound like ethyl chloride and a 1 carbon compound like methyl chloride. Now when I try to do their Wurtz reaction, possibility is there that 2 plus 1 can bind together and become 3. But it's not in our control. Thousands and crores of molecules will be present. So maybe a ethyl chloride may couple with itself to give you a self product butane. Butane will also be formed. Maybe a methyl chloride couple with another methyl chloride give you a ethane. So ethane will also be formed here. That's the reason why propane preparation is not a good method from Wurtz reaction. Okay, so the drawback becomes we cannot use it for the asymmetrical alkanes or any alkane with the odd number carbon. We can't get the product as a major product. It will be like a mixture of different products we get. That's the problem with Wurtz reaction. Another problem is we can never prepare methane from here because coupling में single carbon can never be there as a product. So that's the problem of Wurtz reaction. I hope it is clear to everyone. Moving on to the next one. Now, one more method I can tell you easily, which is if you have alkyl halide, okay, whether aryl halide or alkyl halide, you go from there to Grignard reagent and then hydrolyze the Grignard reagent. So we can mention here another one as hydrolysis of Grignard. When someone says to you something like go from chlorobenzene to benzene, okay, chlorobenzene to benzene, as I've just told you that doing it with, just a second, doing it with zinc plus HCl was not possible because zinc plus HCl cannot reduce aryl halides. So better method is first convert it to Grignard reagent reacted with magnesium in the presence of dry ether, which gives you phenyl magnesium chloride, partial plus partial minus. It's a neat PYQ where after this, if I react it with any proton giving species, any acidic compound, like I can just hydrolyze it, H3O plus may be mentioned, okay, which is nothing but dilute HCl. When we do this, then your phenyl is a negatively charged species, comes out and collects a proton from the H3O plus. Phenyl in a proton becomes benzene. So any alkyl halide you have, you can, or aryl halide you have, you can first do its, preparation of Grignard, and then from Grignard you can just hydrolyze the Grignard. Okay, for this they can mention dilute HCl. They could mention phenol because phenol is also a acidic compound. They could mention H2SO4. They could just mention water, etc. Any of these reagents they can mention, right? All right. So this was from alkyl halides. Then from alcohols, there is no good method of preparation. You can do reduction by red phosphorus HI, but not mentioned in the NCERT. Moving ahead. From aldehyde ketones, in the chapter aldehyde ketones, you will study about reduction, which is Clemmensen reduction and Wolff-Kishner reduction. If you want, you can revise the reactions with me. Clemmensen, zinc amalgam HCl, Wolff-Kishner, hydrazine plus KOH in ethylene glycol. All of you, I hope, remember these reactions. Then going to next chapter, which is carboxylic acids. From carboxylic acids, 2 important methods are given in the NCERT. If you want to prepare alkane with a lesser number of carbon, 1 carbon less, we will go for decarboxylation by soda lime. Decarboxylation by soda lime, which is a carbon ion involving mechanism. Okay, although mechanism is not given in the NCERT, but if any question comes that which is easy to decarboxylate, just remove CO2 and make a carbon ion there. So in this case, CH3 minus carbon ion will be present in the intermediate, as an intermediate. Finally, taking a H plus, it becomes CH4. So it's a carbon ion forming mechanism. If you want to know which carboxylic acid is most readily decarboxylated, just make a carbon ion, remove the CO2, put a minus charge there. Okay. Wherever the carbon ion is more stable will be more readily decarboxylated. Few examples, you can see them in your modules, or I will just show you one example in some time. So sodium salt of carboxylic acid on heating with soda lime, which is mixture of NaOH plus CaO. Here CaO is a drying agent. You can remember it. CaO is a drying agent. Okay, because if any water gets formed here, you will see the water will get formed here during the first step. When you take a carboxylic acid and react it with NaOH, NaOH is a base, carboxylic acid is an acid. Acid plus base will give you this salt plus water. If that water is formed, then your salt will become soluble in water. Okay, it will become a ionic compound, a soluble compound. It will become sodium acetate solution, and then decarboxylation will not happen. Okay, so you don't want the presence of any moisture or water, otherwise this will become soluble. You need your salt in solid state for this reaction to proceed. Okay, so CaO quickly dries up the water as soon as it is formed in the first reaction, and then carries on the reaction like this. So finally we get alkane with one carbon less, and the CO2 which comes out with NaOH, CO2 is a acidic oxide, NaOH is a base, we get a salt finally, sodium carbonate. This is the reaction, decarboxylation by soda lime. What kind of question can be asked from here? Maybe asked like this: which is most readily decarboxylated by soda lime? Most readily decarboxylated by soda lime. This is one. This is another. This is another. And this is the last one. Okay. Which is most readily decarboxylated by soda lime? Means they are asking from where the CO2 can easily get removed. Where is the COOH group can be easily removed? It's a carbon ion mechanism, as I told you. Such compounds, these are called as beta keto acids. Beta keto acids, because this is the alpha carbon to the carboxylic acid, and the beta is a ketone. Remember that whenever a beta position has a ketone group or a aldehyde group or a carboxylic acid group, in that case, these are very readily decarboxylated, because here the carbon ion formed will be highly stabilized by resonance. Okay, will be highly stabilized by resonance. It's a very stable carbon ion. Minus become pi, pi become minus. Very stable intermediate sends this reaction forward very easily. Okay. In the next one, if I see the carbon ion formed is nothing special about it. There is no resonance here. Next one also nothing special, but it's a very poor carbon ion. It's a tertiary carbon ion. As we know, tertiary carbon ions are highly unstable. This carbon ion also nothing special about it. There is no resonance, but still there is some stability coming by minus I. So I think it's clear to you. First one will be most readily decarboxylated. Last one also maybe little better than the second and third. And then this third would be the worst. Slowest rate will be for the third. And this one will be somewhere in the middle. Okay, so the order would be A will be most readily decarboxylated, then D, then B, and then C. Okay, this type of question can be asked. So finally, the product will be just a cyclohexanone, methyl cyclohexane, methyl cyclohexane, cyclohexanone. Okay, so question could also be asked like, which of the following reactants give same product on reaction with soda lime? So I've just shown you, this was a different compound, this was a different compound, but their final product after decarboxylation is same only. Cyclohexanone here, cyclohexanone here. These two are different compounds, but their final product is exactly the same. So two different types of questions I've shown you here: rate of decarboxylation, ease of decarboxylation, and the product, checking the product whether they are same or not. Okay, right? So these are the ones. Next is Kolbe's electrolytic method, which is another free radical mechanism reaction. Kolbe's electrolytic Kolbe's electrolysis of sodium or potassium salt of carboxylic acid. So it's nothing but you take an aqueous solution of your potassium salt of carboxylic acid and electrolyze it. When you electrolyze it, there are two anions present here who will be fighting for anode, which is OH minus versus acetate, CH3COO minus. Acetate has more oxidation potential, something to remember only. So this will go to anode and get oxidized. And at the cathode, H plus is fighting versus Na plus. And in the electrochemistry chapter, all of you have studied H plus has more reduction potential, which is 0, as compared to sodium, which has negative reduction potential. So H plus goes at cathode, gets reduced to hydrogen gas. Acetate goes to anode, gets oxidized to carbon dioxide, and the remaining CH3 group will couple up to become CH3CH3. So it will be giving you a symmetrical alkane always. A symmetrical alkane, not with double number of carbons than the starting material, but double the number of R carbons. So the number of carbons present in the alkyl group, they will double up. In this case, if I start with, for example, ethanoic acid. Ethanoic acid has 2 carbons. Once the COO group goes out, remaining is methyl. Methyl attaches with another methyl, we get a ethane. Okay, another example. If I start with a 5 carbon compound, like a pentanoic acid. Pentanoic acid has 5 carbon. 1 CO2 will go out. Remaining is butane, a butyl group. Butyl will couple up. So give you a 8 carbon compound, not a 10. Okay, so it will be like N minus 1 and then double. N minus 1, if N are the number of carbons initially present with you, do N minus 1, you get a number. Because if I have 5 carbons, 5 minus 1 I will do, because CO2 will go out first. 4, and then I'll double it. 4, 4, 8. So N minus 1 into 2, these many number of carbons will be there in the final product. This can be asked as a factual point that if number of carbons present in the reactant sodium salt of carboxylic acid is N, then how many carbons are there in the final product after Kolbe's electrolysis? You will say 2 times N minus 1 carbons in product. I've just told you the reason why we have done this mathematics. N minus 1 give you alkyl. If N number of carbons are there in the carboxylic acid, if 5 are there, 5 may say 1 will go out as carbon dioxide, remaining are N minus 1, 4. And then coupling will happen between the two radicals. This is the overall reaction. Mechanism is given in the NCERT. I can show you the mechanism here as well. No, I have not written the mechanism here, but it's a simple general mechanism if you want to see. Finally, we get a double carbon alkane. Okay, a double alkyl. Alkyl will couple up here. So this is the one. So finally, the byproduct is going to be NaOH or KOH, which will make your solution basic in nature. So as the electrolysis proceeds, remember pH keeps rising. pH keeps rising. Okay, this is the one. The mechanism goes like this. The mechanism goes like this. So you have taken your sodium salt. At cathode is simple. H plus goes, gains an electron, become hydrogen gas. I can take 2H plus 2 electron H2 gas. This is the cathodic reduction, gain of electron. At anode, oxidation happens. How the oxidation happens is you take RCOO minus. This RCO minus, I'm taking it 2 moles because finally 2 moles are required for the reaction. Each mole may oxygen loses one of the electrons. So this is how oxygen has a complete octet. Here one of the electron oxygen loses. It becomes an oxygen radical. RC double bond O, O radical like this. Right? This is the one because it is 2 moles. So I'm writing it 2 times. So 2 electrons are lost here. 2 electrons are gained there. Electrons are balanced. Then finally what happens is this particular radical which is formed, it further releases CO2 gas like this. Dot become pi So to become a pi bond, here one pi bond is required, where one electron comes from here. One electron comes from this particular bond. One electron goes to R. So you get 2 moles of R radical and 2 CO2. 2 moles of CO2 go out. And this RR radical join together to become alkane. Okay, so I hope it is clear to everyone. This is how the alkane gets formed. So finally, what is remaining in the solution is Na plus lost with the H plus. Na plus lost the game with the H plus. OH minus lost the game with the RCO minus. So they are still there in the solution. So overall reaction become 2H2O electrolyzed with 2RCOONA. Finally, H plus become H2 gas. RCO become RR and 2 moles of CO2. 2 sodiums and 2 hydroxide become 2 NaOH. Overall, this reaction is using 2 Faraday current or 2 Faraday electricity, or 2 Faraday charge I can say, because 2 electrons got cancelled out. So question can be asked from here regarding the electrolysis as well, Faraday's law, that if current and time are given, then what mass of alkane will produce, how many moles of alkane will produce, what volume of hydrogen can produce, and so on, right? So a question can be asked, a nice question can be asked from electrochemistry point of view as well. So this is about it, Kolbe's electrolysis. Okay. Next is physical properties of alkane. Whenever you see a table in the NCERT, try to analyze what the table is saying, right? So when we talk about the physical properties of alkanes, if you see carefully, their boiling point and melting point both increase as the number of carbons increase. Okay, first I'm starting with the physical state. As you can see, methane, ethane, propane, butane, all of their boiling points are below the room temperature, which is 298 Kelvin. Okay, room temperature is 25 degree. So they are all gaseous in nature. They are all gaseous in nature. Up to butane, this is also butane only. Isobutane is also butane. So up to butane, they are gaseous in nature. Okay, so first 4 carbons are gaseous in nature. And then 5 to 17, you will find them to be liquid. 5 to 17 will be liquid. And then 18 onwards will become solid. The state is clear. Solubility, obviously, they are non-polar compounds. So they are insoluble in water, completely insoluble in water. But they are all soluble in organic solvents like benzene or ether or toluene. Okay, so they are soluble in non-polar like CS2, CCl4, benzene, but insoluble in water. When it comes to boiling point, as all of you know, depends on 2 things. It is directly proportional to molar mass, means number of carbons. If number of carbons are same, then boiling point is directly proportional to surface area. Surface area is more when branching is less, so inversely proportional to branching. So more branched alkanes have low boiling point, right? Like if I take a isobutane versus a butane, butane has more surface area, so boiling point of butane will be more. As you can all see it here, this is N-butane 272, this is isobutane 261. This is something to remember. Same way, if I check for isopentane, and N-pentane and neopentane. Neopentane should have the least one. So you can see here, this is neopentane, 282, it is the least. Isopentane, 300. N-pentane is 310, 309. Okay, so I hope it is clear to everyone that in the pentane case also, the neopentane, which is most branched, has least boiling point, then isopentane, then the N-pentane, something like this. Okay, observe this table, you will be able to learn the physical properties better. Now going to the melting point, remember it as a factual point that propane has the least melting point out of all the alkanes. If you look at the value, propane 85.3. 85.3. It is found that odd number carbons do not have very good packing. So melting point depends on packing efficiency. Odd carbons have poor packing, so propane has the least melting point. Propane, then methane, then your ethane, and then it continues normally. Butane, pentane, hexane, heptane, like that. When it comes to melting point, you should remember one more factual, data, which is neopentane has highest melting point as compared to a N-pentane and a isopentane. Okay, this is something you should remember. Neopentane looks like a very symmetrical molecule. It has very good packing. So in the boiling point, it was at last position, but in the melting point, it is on the top position, because for melting, solids packing is checked. For boiling, surface area is checked. So its surface area is very poor. They can ask a question, and NCERT mentions it has a spherical surface, sphere-like surface. It looks like a ball. Poor surface area, poor force of attraction, poor boiling point. But because of its symmetry, good packing is there. This is one order you should remember. This is one order you should remember. You can see the values, all of you. If I take the neopentane, 256 is the melting point, which is very high. 256 for this one. 256 Kelvin for this one. When I look at isopentane, 113 Kelvin, very, very less, 113 Kelvin. And for the normal pentane, it's 143 Kelvin. So I hope all of you are able to see and remember these facts. Moving ahead to the chemical properties. The most important chemical property of alkane, although alkanes are very unreactive, as all of you know, because there is nothing to react. There is no functional group. There is no polarity between any carbon-carbon bond or carbon-hydrogen bond. So they are very, very less reactive. If you want alkanes to react, majorly they have one or two reactions which are important. One is substitution, which is a free radical substitution reaction, or we call them as halogenation, substitution reaction. The most important reaction is this one, as it follows a free radical mechanism. Every free radical mechanism, all of you know, has 3 steps. Initiation, to start the reaction, propagation, to pass the radical from one molecule to another, and then termination. Okay, these are the 3 steps which are there. What is the reaction? Take any alkane, react it with halogen gas in the presence of sunlight or high temperature. Okay, so one or more hydrogen atoms of alkanes can be replaced, means substituted, by halogens or nitro group also, or sulfonic acid group also. These reactions are not mentioned in the NCERT, only halogenation is mentioned, so that is important for us. Halogenation takes place either at high temperature, around 300 degrees to 500 degrees Celsius, or in the presence of diffuse sunlight. H nu may be mentioned, or UV light. Okay, UV may be mentioned, H nu as a photons may be mentioned. Lower alkanes do not undergo nitration and sulfonation. So methane, ethane, propane do not undergo nitration, sulfonation. Reactions in which hydrogen of alkanes are substituted by halogens is called as substitution reactions. Okay, now coming to rate of reactivity. Whenever you will find any halogen reacting in a reaction, F2Cl2Br2, fluorination will always be very fast as compared to iodination. It is completely based on their reactivity order. Fluorine is a much more reactive halogen than iodine, as all of you know. You studied in you study in the group 17 that fluorine is the best oxidizing agent. It has the highest SRP, so it's most reactive in nature. So fluorination is explosive, remember it. Iodination is slow and reversible. So to do iodination, we take help of external agents, which are oxidizing agents like HNO3 or HiO3. Few facts to learn. And because it's a radical mechanism, radicals are very stable on allylic carbons due to resonance, or tertiary carbons due to hyperconjugation. So allylic, tertiary, secondary, primary, this would be the order of reactivity. Allylic will be more reactive than tertiary as well. Allylic, benzylic will be highly reactive. So whenever you're doing a halogenation and you want to see what is the major product, then always try to remove a hydrogen which is present on a allylic position. If you don't have a allylic position, remove it from the tertiary position. If tertiary is not available, then secondary, and then primary, so on. Okay, this is about the iodination written. When we do iodination, it's a reversible process. So if I want to send this reaction forward, I need to remove this HI which is formed. Right? Then by Le-Chatelier principle, reaction will keep going forward if I remove the HI. To remove the HI, we use an oxidizing agent like HNO3, which can remove the HI. Okay, or HiO3 also we can use, which is also oxidizing agent. So what happens is it oxidizes HI back to iodine, which increases the yield of reaction. Okay, HI is removed. If HI is removed, Le-Chatelier says send the reaction forward. And also iodine is increased. Iodine increased, Le-Chatelier say send the reaction forward. So reaction goes more and more forward. That is the problem with iodination, that it is slow and reversible. I hope it is clear to all of you. Okay, this is the mechanism. Mechanism is not mentioned here by me. I'll just show it to you. So the problem with halogenation is that you cannot control the reaction to give a single product. There are multiple number of products that you get always in a free radical reaction. It's very difficult to control these reactions. So they will always mention one equivalent chlorine is taken or two equivalents are taken. If one equivalent is mentioned, then you can do one-time substitution. One hydrogen you can remove. If two equivalents are mentioned, then you will get a dichloro product. If three equivalents are mentioned, trichloro. If excess is mentioned, then all the hydrogens can get substituted by chlorine. Because in the propagation step, you will see that each hydrogen has a possibility to get abstracted, right? So this is about our halogenation reaction. Now we'll see some problems which come from this topic before moving ahead, right? So it's a NEET PYQ to 2025, which is just the last year's PYQ. How many monohalogenation products are expected? Monochlorination products are expected from isopentane. Okay, very nice question. Too many times repeated same type of question. So when I do chlorination, one equivalent. As you can see, I can attack a chlorine here, one position, here second position, here third position, here fourth position. This is also same only because these two carbons are exactly the identical. Whether I put a chlorine here or here, same product I will get. So four products come out from here. Structural products are four. 1, 2, 3, 4. In one of the product, chlorine attacks here. In one of the product, chlorine attacks here. Third one here. Fourth one here. Including stereo. To check stereo, I should check for geometrical isomerism first. Not possible because there is no alkene here. There is no cyclo compound here. Then I'll check for the optical isomerism, for which we require a chiral carbon. Here if I see, this carbon has 2 methyl, not chiral, 2 hydrogen, not chiral. Here this carbon becomes a chiral carbon. It has 1 hydrogen, 1 methyl, 1 isopropyl and a chlorine. 1 chiral carbon is present. 1 chiral carbon means 2 to the power 1. It will have 2 isomer, dextro and levo. Right? Moving on to the next one. Here nothing is chiral because CH2, CH3 and this one has 2 methyl. So it's a single product. Here this carbon is not chiral, but this carbon became chiral. After the chlorination was done here, the second carbon became a chiral carbon. It has a hydrogen, it has a methyl group, a CHCl group and a ethyl group. So it will also be 2 to the power 1, 2 isomer, dextro, levo. So we get 1, 2, 3, 4, 5, 6, 6 isomers total are possible. right? I hope it is clear. Moving ahead. Another PYQ that I've taken here. Very nice PYQ from the physical properties. All questions will be derived from NCERT itself with some extra points. Okay. So boiling point of the three isomeric pentanes are in order N-pentane boiling point, not melting. Iso, neo. Absolutely correct. Correct statement. When branching increases, the molecule attains a shape of sphere. Exactly correct. Whatever the NCERT says they have mentioned. This results in smaller surface area. Yes, that is correct. And due to which the intermolecular force of attractions between the spherical molecules are weak. Absolutely correct. Therefore, lowering the boiling point. Absolutely correct. So both are correct statements. Both the statements are absolutely correct. Right? So these are the important questions asked from the alkanes. Again, a decreasing order of boiling point they are asking. Another question from NEET 2022. Decreasing order of boiling point. Okay. First thing, always check number of carbons. More the carbons, more the boiling point. 7 carbon heptane, butane 4 carbon, methyl butane 5 carbon, methyl propane 4 carbon, hexane 6 carbon. So directly we can see A goes to the highest, then goes E, 6 carbon, then 5 carbon, C, AEC, AEC, first option. Right, like this, try to, judge for the best option quickly. This is about this question. Next is again a question of NEET 2016, which is compound, this is a good question. Many students have done mistake here. Which compound reacts most readily with gaseous bromine? Gaseous bromines mean again free radical substitution reaction. I need to check where can I see the most stable radical, and that will be most reactive. C3H6 means propene. C2H2 means ethyne. C4H10 may mean butane or may mean isobutane. Okay. C2H4 would mean ethene. Question is, who reacts most readily with the gaseous bromine? It's a nice question. Many people answered this one thinking that it's a tertiary, or many people answered these thinking that a bromine liquid is taken and maybe they are doing test for unsaturation. It's not bromine liquid. If it was written as Br2 liquid in the presence of CCl4, that would be test for unsaturation. Then also this only will react faster. As a alkene, it is a more substituted alkene, it will react faster. But they are not asking about this reaction. They are asking about Br2 gas, which is only possible at high temperature, 553 Kelvin, like that. Here the free radical formed will be very stable. Allylic free radical I can see. So this will be the highly reactive one, because allylic radical is possible here. So when I react it, I get a very stable radical, which gives us the final product, 3-bromo propene. Okay. Then second best would be this one, because tertiary is present here. But they didn't mention which butane. So giving a benefit of doubt, maybe this one. Even if it was isobutane, still our answer would remain as allylic position to be more reactive. That's why I told you during halogenation, always check allylic first, then tertiary, secondary, and primary. This would be least reactive here, because a radical is never stable on a sp carbon or a alkynic carbon. A radical is never ever stable. Moving on to the next type of chemical properties of alkane, which is going to be combustion. All of us know about combustion. Alkanes and alkenes and alkynes are used as fuels because their combustion is highly exothermic. More the number of carbons, you should remember that combustion is better. That's why the commercially used fuels like butane, which is there in the LPG, and the heptane and octane, which are there in the petrol, have a lot of carbons. Also, you should remember, more the primary methyl groups, better is the combustion. So isooctane is one of the best fuel used in the petrol. the general combustion reaction we should remember. If you do insufficient amount of oxygen if we give, then incomplete combustion will happen, which is going to produce either carbon black, which is the sooty flame that you see, the black fumes that you see, or even carbon monoxide also get formed, which is a very dangerous and harmful gas. If carbon black is formed, that carbon black is used in inks and the printer inks and black pigments like shoe polish and everything as filters, right? Next is controlled oxidation. This is one of the important reaction, catalytic oxidation. If you use particularly these three reactions are there. If methane's oxidation is done in the presence of copper at 523 Kelvin and 100 atm, remember the condition, very important. Whichever conditions are given in the NCERT, we have to remember them as it is. Then its partial oxidation gives you alcohol, methanol. If I use molybdenum trioxide, we get methanol, aldehyde. If we use manganese acetate with ethane, we get the ethanoic acid. Three reactions, just learn them as it is. Methane to methanol, methane to methanol, ethane to ethanoic acid using the three catalysts. Generally, alkanes are not oxidized by KMNO4, but if a alkane contains a tertiary hydrogen, it will be oxidized to an alcohol. This is also an important point. Like isobutane they have taken. Isobutane has a tertiary hydrogen available. There the oxygen can insert and give you a tertiary alkanol. Okay. These are the reactions which are there for the oxidation. Apart from this, you can see isomerization reaction. Whenever you take anhydrous AlCl3, any alkane can give a rearrangement reaction to give you different chain isomers. So hexane can isomerize to give 2-methylpentane, 3-methylpentane, even neohexane also it can give, and all the byproducts which are possible. These are not great reactions obviously because so many byproducts are there. So no type of question can be asked from isomerization. Maybe a isomerization of butane may be asked, which can give you isobutane, because here a single product is possible. This can be asked. So alkanes on heating in the presence of anhydrous AlCl3 and HCl gas isomerize to branched chain alkanes. Major products are given below. Some minor products are also possible, which we can think over easily. Next one, aromatization. Another very, very important reaction for the preparation of benzene and benzene derivative. If you take a hexane or a heptane or octane, first and sixth carbon can undergo cyclization by removal of hydrogen gas. So if I remove a H2 gas from here, I can reach to a cyclohexane. And further 3 times if I remove more hydrogens from cyclohexane, if 3 unsaturations more I try to go and give it, it can convert to benzene by removing 3 more moles of hydrogen gas, which can be carried out in the presence of a few catalysts like aluminium oxide is a must, Al2O3, and also in the presence of oxides of some D block elements. You can see them here at high temperature of 773 Kelvin, which is 500 degrees Celsius, 10 to 20 at atm pressure. Whenever N alkanes of 6 or more carbons is heated at high pressure in the presence of oxides of vanadium, molybdenum, chromium, V2O5, MO2O3, Cr2O3, supported over Al2O3, alumina. Remember this. It is dehydrogenated 4 times to give you aromatic product. We can also call it reformation reaction, reformation reaction. Okay, this is the name of this reaction. So hexane gives you benzene. Same way heptane will give you toluene. Same way octane can give you ethyl benzene. Right? So these are the ones. Next is reaction with steam. Another reaction where the reagents are more important. The catalysts are more important. Methane, when react with steam H2O gas, it gives you carbon monoxide plus H2 1:3 ratio, which is called as syngas. Syngas. Methane reacts with steam at 1273 Kelvin, 1000 degrees Celsius, in the presence of nickel catalyst to form carbon monoxide and dihydrogen. This method is used for the preparation of dihydrogen gas. So when the hydrogen chapter was there, it was one of the method to prepare H2 gas. Last is pyrolysis. Pyrolysis is a reaction also called as cracking, where you take a big alkane and just heat it strongly. It breaks down into smaller hydrocarbons. If you make one alkane as a product, other will automatically become alkene. For example, if I take C6H14, which is hexane, it can give you hexene plus hydrogen. Just balance the atoms. It can give you something like a butene, 4 carbon ka alkene, so other 2 carbon automatically will become alkane. 1 ene, 1 ane. 4 ka ene, then 2 ka ane. If you make a 2 ene, then 4 ane automatically. If you make a ethene, then butane will be the byproduct. Propene. Okay, so they are breaking into 3. If I break into methane plus ethene plus propene, just balance the total carbons and hydrogens. Not a very, very important reaction because you can't predict the products here. Okay, so nothing can be asked from here from pyrolysis as well. Looking at few PYQs from these topics, from the alkanes, you can see here it is a MO203 they have taken at 773 Kelvin, directly J mains question 2021. Aromatization 1, 2, 3, 4, 5, 6. So if I do the aromatization here, this methyl will be hanging outside, giving you a toluene, D option. Next is going towards the last two topics, which is alkene and alkynes. Alkenes and alkynes are much more reactive than alkanes, so they have a lot of chemical properties, as you all know, like addition reactions and oxidation reactions. These are two major ones. Now, how to prepare alkene and alkyne? First, we'll prepare alkenes quickly, and then we'll think of alkynes. To prepare alkenes, two methods I already told you. Start from alkyne. If you want to go to a cis alkene, you can add hydrogen in the presence of pelletized carbon, which is Lindlar's catalyst. It gives you syn addition. Syn addition means same side attack. Both the hydrogen attack from the same side, giving you a cis alkene. Right? Reaction stops here. Pelletized charcoal is a deactivated palladium. It is not so reactive that it can take the reaction to alkane. It stops at alkene. Or you can take sodium in the presence of liquid ammonia if we want the hydrogens to attack from the opposite side. That will be a anti-addition. Anti-addition. And trans-alkene gets formed here. Actually here H2 gas is not required. All the hydrogens come from ammonia only. So by mistake NCERT has mentioned H2 here. Just Na liquid ammonia is required. Right? So this is the one. Two examples are written. Ethyne to ethene, propyne to propene, butine to cis-butene, and butene to trans-butene also you can prepare from here. Okay, moving ahead. Next important preparations of alkenes come from alkyl halides and dihalides. When you take monohalide, something like a chloroethane, the removal of HX is done. HCl we have to remove, so we call it dehydrohalogenation. Dehydrohalogenation is the name of the reaction, which requires a base. Dehydrohalogenation using a base like alcoholic potassium hydroxide. Potassium hydroxide dissolved in alcohol. You can take bulkier bases as well. If you take small base like a hydroxide or a ethoxide or a methoxide, these are called as small sized bases. Alcoholic KOH may be mentioned, alcoholic KOET like potassium ethoxide may be mentioned, or methoxide. Then you will get a ZZEF product as the major product, which is the more substituted alkene. But when we take a bulkier base like potassium tertiary butoxide, in that case a Hofmann product, the less substituted alkene, becomes the major product. So one example I'll show you for this, and we'll move ahead with this. One example, let us see. Like if I start with a haloalkane, which is 2-bromobutane. If I reacted with alcoholic KOH, or if I react with alcoholic potassium tertiary butoxide, okay, all of you know this, so it's a, as you know, it's a recap capsule that we are giving you, so we are not telling the exact pull in depth because that much time is not there now. So I'm just quickly telling you this is a beta carbon, this is a beta carbon, this hydrogen is available, and here also a beta hydrogen is available. Since it is a E2 mechanism, it's an anti-periplanar mechanism, means the hydrogen and the bromine must be present anti to each other, means opposite side to each other. So I'm showing it like this. Okay. If you take a small sized base, it can easily attack on beta protons, which are even embedded deep inside the molecule, like this one. Sigma become pi, Br minus goes out, and you get your major product as a better alkene, which is a ZZF product. But when we take bulky bases like this, attacking inside in the depth of the molecule is little tough because of steric hindrance. So it attacks instead on the outer protons like this. So now the sigma become pi and Br minus goes out, gives you a Hofmann as the major product. Hofmann product major. The alkene which looks less stable is formed as the major product. It's E2 mechanism. E2 mechanism is bimolecular elimination. It doesn't have any kind of rearrangement. It's just an anti-periplanar mechanism where the hydrogen and bromine must be present in the opposite sides in the same plane. This is something that we should know about it. Okay, this is beta elimination reaction. I've already told you about it. Reactivity is always better for the iodides, then bromides, then chlorides. Iodide being a very good leaving group, big size, it has very weak bond with the carbon. So iodine being a very good leaving group, I minus, the reaction is best with the iodides. And fluorides don't even react it here. They react with a different mechanism, E1CB mechanism. And always the reaction is going to be best with the tertiary alkyl halide. Okay, E2 mechanism is best with the tertiary alkyl halides because tertiary halides will give you much better alkene, much more substituted alkene than a primary one. So if I take a tertiary alkyl halide like this, if I take a secondary alkyl halide like this, if I take a primary alkyl halide like this is going to give us this alkene, it is going to give us this alkene, it is going to give us this alkene. As you can see here easily, the first alkene is most stable because of too much hyperconjugation, 3 alpha here, 3 here, 3 here. Then second one is also good. Third one, not so great. So reactivity will be fastest for the tertiary, then secondary, then primary. So this is most reactive. This is least reactive. Okay. This is about the E2 mechanism. Next is, if you have a dihalide, then I already told you, if you have a geminal dihalide, 1,1 dihalide, then you can do coupling with the zinc. Okay, that one I have not shown here again. So if the coupling reaction as I just showed you, if you have a geminal dihalide, already in the alkanes chapter I told you. But if you have a vicinal dihalide, then you can use again the same thing, zinc in the presence of ethanol. Same thing will happen, Br2 will go out and you get a alkene. And you will get a alkene. Okay, dehalogenation reaction we call it. Instead of using zinc, you can also use NaI in acetone, which is same as your Finkelstein reaction. Actually, when 2 times Finkelstein reaction will happen, one iodine will come here, one iodine will come here. 2 iodines next to each other on the adjacent carbon are unstable. So automatically I2 gets released and you get a double bond here. Okay, so when you take a vicinal dihalide to remove the Br2, you can take zinc. It is also anti-periplanar mechanism. Please remember it. It is anti-periplanar. Means only when the 2 bromines are opposite side, they can be removed. If they are on the same side, they can't be removed. If I take a Br here, for example, out of the board, a Br here, for example, out of the board, and I put zinc here, nothing will happen. Nothing will happen. The BRs must be opposite side. So if I take a BR on the front, means out of the board, one BR at behind the board. Yes, now if you react with zinc and heat, this time the alkene will get formed. Okay, something to remember here. Addition of bromine is also anti-periplanar. Okay, if I add bromine, Br2 in the presence of CCl4, Also, the two bromines go in the opposite planes only. They never go on the same side of the plane. Okay, on the opposite sides they go. So remember it. Addition of bromine into alkenes is also a anti addition mechanism. Removal of Br2 using zinc is also anti-periplanar elimination. Dehalogenation we call it. Dihalides in which two halogens are attached to adjacent carbon atoms, neighbors, are known as vicinal dihalides. Vicinal dihalides, this one is named as ethylene bromide. Ethylene bromide, not dibromide, ethylene bromide. And the geminal is called as lidene, ethylidene bromide. Okay, so 1,1 dibromoethane is ethylidene bromide, 1,2 is ethylene bromide. On treatment with zinc metal, lose molecule ZnX2 to form a alkene. Next one, very, very important, E1 mechanism. Dehydration of alcohol. Wherever 1 will be written on the head of a mechanism, E1, SN1, they are some headache type mechanism, means they have possibility of rearrangement. So making the product becomes a little tricky there. Okay, so you need to know how to do the carbocation rearrangement. Whenever you take an alcohol and heat it strongly at 170 degree with concentrated H2SO4, 170 degrees Celsius, or concentrated H3PO4 at 250 degrees Celsius. Both are same. You are going to get a alkene, which is Sedzef alkene, but with rearrangement. In the NCERT, they have not shown any example of rearrangement here, but I will show you one example. So kindly look at that. So this is the thing written about it. I've already told you all these things. So we'll see the example of one elimination using concentrated H2SO4. For example, if I have this particular alcohol and it is treated with concentrated H2SO4 170 degrees Celsius. One of the famous question which NEET asks is this one, and one is this one. Heated with concentrated H2SO4 170 degrees Celsius or 343 Kelvin. Right, 443 Kelvin 443 Kelvin. So when you take these two examples, first thing you do is do the mechanism properly. It's an E1 mechanism where the alcohol gets protonated by taking the H plus from H2SO4. Taking the H plus from H2SO4. So H plus comes out from here. HSO4 minus goes away, giving you the protonated alcohol. And we know water is a good leaving group. So from here, water leaves directly, giving you a carbocation formation. Okay, whenever carbocation is formed, it tends to rearrange. A carbocation next to a 5-membered ring, ask the neighbor, you take my plus, give me your 2 electrons. So the ring expansion happens here, as all of you know. So we'll expand the ring like this. Carbocation just outside the 5-membered ring tends to rearrange to a 6-membered ring, because 6-membered rings have less angle strain. Okay, they are more stable rings. So this bond cleaves from here and finally given to that carbon like this. This carbon becomes the carbocation. This carbocation is secondary. It will further do one more hydride shift from here like this, 1,2 hydride shift, to finally give you a tertiary carbocation like this. Okay, so all this rearrangement, please be very careful with. You need to remember how to, you need to know how to rearrange your carbocations in order to make the product. Now the alkene will form finally HSO4 minus, which acts like a base, takes your beta proton, giving you a Sedzef stable alkene. So a rearranged product is formed like this. Since it's a E1 mechanism, it will undergo a rearrangement. So when ring is there, ring expansion can be done. Here in this case, first thing, OH takes up the H plus, water goes out, giving you a carbocation which looks like this. Carbocation is secondary here. Ask the neighbor, do you want my plus? Neighbor says, yes, I am tertiary. I can take your plus. Send me one of the group. It has only methyl, so I'm sending the methyl from here. Methyl shift we will do, giving you a tertiary carbocation, which looks like this. Okay, and the H was also here, so I'm showing the H here. So this carbocation, then now it will lose the proton, so deprotonation. HSO4 minus goes and remove the proton from here, the beta proton. Sigma become pi, giving you the rearranged alkene. Like this. Okay, so if we don't know about the E1 mechanism, we will make a wrong product here. We will remove a H from here, giving you a different alkene, which is not the major product. This is how we can predict major product of elimination. These are the methods of preparation for alkenes. Now alkynes. If you want to prepare alkynes, same thing you can do, just one time extra, so that you can get one more pi bond. Alkynes are nothing but alkenes ka bigger brother, which have one more pi bond. So similar methods can continue when you take a dihalide, vicinal dihalide, or geminal also you can take. You want to do dehydrohalogenation, but 2 times. So first time dehydrohalogenation can be done with alcoholic KOH, same reaction. Okay, one time bromine will go out, one time hydrogen will go out, giving you a alkene. It will give you a vinyl halide. Then next time when you want to remove one more HBr, you need a stronger base. Okay, vinyl bromides are not very reactive towards elimination, so you require a very strong base like sodamide. Remember it, sodamide, NaNH2, heating. So when you heat with NaNH2, this time NH2 minus takes out the beta proton, sigma become pi, Br minus goes out, giving you finally alkyne. So from a monohalide you can't reach to alkyne directly. From a monohalide you will reach to alkene only. But when we have a dihalide, then we can do 2 times dehydrohalogenation to get a alkyne. Okay. Another important method just to prepare propine, to prepare ethyne is from calcium carbide, CaC2. So NCERT has written it. All the reagents are important. Take calcium carbonate, prepare quicklime from there. Okay. So calcium carbonate of limestone is taken, heated to get the quicklime. Quicklime reacts with carbon, heat it, you get CaC2, calcium carbide, which contains ionic bond also, Ca plus 2 with C2, 2 minus, like this, calcium carbide. Calcium carbide hydrolyzed, just put into water. Calcium takes away the OH minus, giving you COH whole twice. And the 2H plus go to the carbide group, giving you ethane. Okay, this is the preparation of ethyne from calcium carbide, CaC2. Okay, so this is the one. Nothing special written about it here. Now let's continue with some of the questions. Right. So the questions which are asked in the previous years from the preparation of alkenes and alkynes. They are saying trans 2-phenyl 1-bromocyclopentane. Trans 2-phenyl 1-bromocyclopentane. So we have taken a cyclopentane. 2-phenyl 1-bromo. So there is a bromo here. I am keeping it outside of the board. Since it is trans, that means the phenyl is behind the board here. This is the compound on reaction with alcoholic KOH. Okay, so it's a very good question. It's a engineering question. I told you that E2 mechanism is anti-periplanar. Means it can only pick up a proton from beta carbon if the proton is opposite to the bromine side. If it is on the same side, it can never pick up a proton. So here this proton has to be front of the board because phenyl is behind the board. This proton is not applicable to be picked in E2 mechanism because it is on the same side of bromine. Both the proton and bromine are coming out of your notebook, so they cannot be picked together. So we can't make a product from here, although the product will be very stable if I get it here. But I can't make it because it's the same side. So I have to take out a hydrogen from here, which is behind the board. There is one out of the board as well, but we'll leave it. This is also not applicable. This one is applicable. So this proton has to be removed. OH minus attacks on the proton. Sigma become pi. Br minus goes out, giving you this product. This phenyl stays behind the board and a pi bond comes here. Okay, a good reaction. So we get what? We get a 1, 2, 3. 3 phenyl cyclopentanone. It's a nice question. Okay. If you try to do it faster, you may get this answer, but this is the wrong answer. You need to know that E2 mechanism is anti-periplanar mechanism. Next one. Which reagent gives you alkyne? I can see it's a dihalide, not a tetrahalide. If it was a tetrahalide, I could use zinc. If it was a tetrahalide, I could use zinc 2 times. Zinc will take out ZnCl2 from here. Zinc will take out ZnCl2 first time like this, anti-periplanar. Second time like this. And I can get the alkyne if it was a tetrahalide. So I can't use zinc here because it's not a tetrahalide. They have given us a dihalide, so I have to use alcoholic KOH in ethanol. Although second step will require sodium amide, but they have not mentioned it, so best option we can choose here. At very high temperature, second step KOH can also be used, but that requires extreme conditions. Okay. So this is the one. Now coming to the chemical properties of alkenes and alkynes. Major properties that they show are addition reactions. Okay. Because they have a pi bond, so they are electron rich in nature. So electrophiles add on them very readily. Electrophiles are electron loving species, mostly H plus or a Br plus. They will add on them, giving you electrophilic addition reaction. Electrophilic addition reactions become very important when they have carbocation formation taking place, because then rearrangement tend to happen. So whenever you add HBr, HCl or water into alkene, these are the reactions which are rearrangement possible reactions. Other reactions like addition of bromine liquid doesn't have any rearrangement. It has a different mechanism called as a cyclic halonium mechanism, not required for us right now. So rearrangement is possible when you add HBr, HI, HCl, or you add water in the presence of H2SO4. Those become more important reactions. So I've taken them first. Addition of water. Addition of water takes place by Markovnikov rule, but never follow the Markovnikov rule blindly, because you can get wrong products. Markovnikov said that the positive part H plus and the negative part OH minus. H plus adds to carbon having more number of hydrogen, which is here. OH minus adds to part carbon having less number of hydrogen, which is here. Which is true for a simple molecule like a propene or a butanene and so on. But as soon as alkenes become bulkier, rearrangements tend to happen, and you will not be able to get the correct product by Markovnikov rule. Okay, one example again I'm giving here where the rearrangement may be required. For example, if I take this particular alkene, CH3, CH, CH3, CH double bond, CH2. Okay, a 3-methyl butanene I have taken, and I do addition of water, for which you require water in the presence of a few drops of H2SO4, dilute sulfuric acid. Okay, what happens is alkene is electron rich, first takes up the H plus, giving you a carbocation on the secondary carbon. So first step of Markovnikov is followed correctly, that this proton attaches to this corner carbon so that a carbocation can be formed secondary, which is better than primary. So I have two options. If I attach the H here, I get a plus here, which is good. Or I attach a H here, which I get a plus on primary, which is not good. So I have done this. Carbocation always tend to rearrange. Ask the neighbor, do you want my plus? Neighbor says, yes, I am tertiary. I am sending you a hydride. You keep my H minus. Give me your carbocation. This type of rearrangement will happen. I hope it is clear to all of you how to do the hydride shift here. H minus along with the electron shifts here. Hydride shift. Now the water comes to add, and finally OH attaches here, giving you a rearranged product like this. Okay. If you did not know the shifting, then you might have just put a OH here, which would have given you a 3-methyl butane tool, which is not a correct answer. Answer is 2-methyl butane tool, which is a rearranged product. So take care of these things. Same thing happen in the addition of HBr, HCl, HI. HI will add most readily whenever the reaction comes with hydrogen halides. Then HI will be the best reactor because HI is most acidic in nature. It can easily give its H+. But when reaction comes to halogens as a reactant, then fluorination will be faster, iodination will be super slow. Okay, so this is the one. So you should remember how to make the product. Same thing would happen if I add HBr. Carbocation will form, carbocation will shift, then Br will attack here. Okay, so this is about addition of HBr. What is Markovnikov rule? I have already told you. Okay, and how to make the carbocation and the major and the minor product I've already explained to you. One example more I'll show you here. For example, if I have this particular alkene and I try to add HBr into it. HBr has partial positive hydrogen, partial negative bromine. Alkene is electron rich, attacks on the H+. Br minus goes out from here, which will be used in the last step to attach to carbocation. This carbocation gets formed. By Markovnikov rule, hydrogen has attached to this corner where two hydrogens were already there with the carbon. Now rearrangement I told you already. Carbocation asks the pair, next carbon, hi neighbor, do you want my plus? Neighbor says yes, because I am tertiary. I can give you my hydride. Carbocation says don't give me your hydride. If you give me your hydride, although we get a tertiary carbocation, but the carbocation comes on a pentagon. On a pentagon, angle maximum possible is 108 degree. But carbocations are sp2. They require 120 degree angle. So this is not good. They say, don't give me your hydride. Keep your hydride. Give me the other bond, which is this one. Now I feel happy because you have just converted me to a 6-membered ring. Now I have a 120 degree angle. Now I am happy. Since I will do one more hydride shift because I can reach to tertiary now. Each hydride shift should reach to a better carbocation, please remember. And now the Br minus comes to attack, finally giving you a rearranged product, 1-bromo, 1-methyl cyclohexane. All these are important and PYQs, important reactions, and they are the PYQs. Anti-Markovnikov rule is when you follow the Markovnikov exactly in the opposite way, where the carbon with more hydrogens actually get the halogen and carbon with the lesser hydrogen gets the hydrogen, which is only shown by one and only one of the hydrogen halide, which is HBr. HCl, HI do not show anti-Markovnikov rule or Kharash effect because of non-feasibility or endothermic nature of few steps. So we can just see here, when we take HBr in the presence of peroxide, we call it as peroxide effect or Kharash effect or anti-Markovnikov addition. In the presence of peroxide, addition of HBr to unsymmetrical alkenes like propene takes place contrary to Markovnikov rule, means opposite to Markovnikov rule. This happens only with HBr, not with HCl and HI. This addition reaction was observed by Kharash and Mayo in 1933. Some things are given. This reaction is also known as peroxide effect or Kharash effect. Final product I can see here. This carbon carries two hydrogens, so Br will go and attack here, H will go and attack here. It's a free radical mechanism. It's a free radical mechanism. Mechanism is also mentioned here. You can see first thing is in the presence of peroxide and sunlight. First, this peroxide is used as an initiator to initiate the reaction. Is the initiator. It first homolytically cleaves because peroxide has a linkage between O and O, which is not having any electronegativity difference. This bond can be easily homolytically cleaved. It will be cleaved on heating or in the presence of sunlight to give you two radicals. Okay, benzoyl radical we'll call it because it's benzoyl peroxide I've taken. This benzoyl radical then further rearranges like this, like the rearrangement or like the decarboxylation we did in the Kolbe's electrolysis, where this dot comes here, become pi, one electron taken from here, one electron goes here, giving you a phenyl radical. This is the initiator for us now. Phenyl radical goes to HBr, take a H radical from here, produces a Br radical. This Br radical propagates the reaction further. It goes to your alkene. Says alkene, you dissociate homolytically. If I attach to corner, radical formed secondary, which is good. If I attach to middle, radical will be formed primary, not good. So let me go and attach to corner like this. Finally giving you a secondary radical, which is stable. This is unstable. So automatically we are following anti-Markovnikov. Br will always go to carbon having more number of hydrogens so that a radical can be formed inside. Okay, radical can be formed on a carbon with more hyperconjugation. So this is a good radical, more stable secondary radical. Now it will go to another HBr and collect a H radical from here, giving you the anti-Markovnikov product. Okay, this is the one. When it comes to other additions do not take place with any rearrangement. So they are more on the easier side, like addition of bromine used as a test for unsaturation. The two Brs must be attacked on the opposite side. They have written same side by mistake here because anyways in an alkane, if final product is a single bond, the rotation is allowed. They can keep rotating. So there's no problem. You can show same side, opposite side. But if it was a ring, you must show the two bromine on the opposite sides to each other. It's anti-addition mechanism used for the test of unsaturation. Orange color of the bromine is decolorized by alkenes as well as alkynes, but not by benzene. So benzene doesn't give this test. Benzene plus Br2, no reaction. Benzene plus Br2CCl4, nothing will happen. Right? So these are the one. Next is addition of cold sulfuric acid. Cold concentrated sulfuric acid adds to alkenes in accordance with Markovnikov rule to form alkyl hydrogen sulfate. So when you take cold concentrated sulfuric acid, in that case H plus and HSO4 minus will add by Markovnikov rule. So here H plus to one of the carbon I'm giving, other carbon takes the OSO3H. This is the one. If I heat it further, again it will become alcohol because same reaction was there, the hydration reaction, where also you were taking sulfuric acid, but that was dilute sulfuric acid, majorly water. Here we have taken only sulfuric acid, no water present. So we say concentrated sulfuric acid. Okay, so this is the one. Addition of dihydrogen, already this reaction that I have told you. Addition of halogens to the alkyne you can do. Same thing, same chemical properties of alkynes now I'm showing you. Alkynes to alkanes, alkynes to alkanes, alkynes to tetrahalides. If you add bromine 2 times, it will add. Addition of HX again 2 times. Same Markovnikov rule, same to same. Here also carbocation will form. The vinyl carbocation will form here. Vinyl carbocation. So in the first step, when it attacks on H plus, you get a vinyl carbocation. And then the Br minus attacks here. Like this. They are much lesser reactive as compared to, alkenes for the addition reactions, because here the carbocation is not good. Vinyl carbocation is not stable. Number 1. Okay. Number 2, alkyne carbons are sp nature carbons, which are highly electronegative. So they tend to keep their pi electrons to themselves. They don't want to donate their electron. Okay. So that's why Alkynes are less reactive towards addition. HBr will add 2 times with the Markovnikov rule to get your final product. Addition of water, important. Very important reaction. Addition of water into the alkyne. Whenever you take a alkyne, like a ethyne or something like a but-1-ine. First of all, you require dilute sulfuric acid. You also require mercuric sulfate as a catalyst here at 333 Kelvin, okay, which is 60 degrees Celsius. Water adds once only to give you a enol. So OH goes to one of the carbon, H goes to one of the carbon. Enol then tautomerizes to become aldehyde or ketone. In this case, it will become acetaldehyde. So only one alkyne gives you aldehyde, which is this one, acetaldehyde. Other alkynes will always give you ketone. You can see by the Markovnikov rule yourself. H will attack here. OH minus will add here. Obviously by Markovnikov rule. So always the oxygen goes in the middle, not on the corners. So you get a ketones always. So a statement type question can be asked that only ethyne gives the aldehyde on hydration. Other all alkynes give ketone. It's a correct statement, right? This is the one. All right. This is all about the chemical properties. One more is there after this, which is going to be ozonolysis, which is also very important and the favorite reactions of, paper setters. This reaction I've already shown you. You can tell me the product in the chat box. What is the answer for this question? I'll call this question as question homework A. Homework question A. What is your homework question number 1? Pause the video here. Okay. Draw the product and write in the comment box what is the answer for question number 1 of the homework. Okay. Pause the video. Do it yourself. A nice question. You need to tell me the answer yourself. Next one. I've just told you this question as well. Again, homework number 2. Tell me the answer in the comment box. It's a AIPMT question. Means again a NEET question. Already we have done. I just showed you. Another good question. Homework question number 3. Very, very good question. Or instead of giving you a homework, a hint I can give here. A hint I can give here. You are doing hydration of alkyne. Hydration of alkyne. Hint is, it is a carbocation mechanism. You need to think, after breaking this pi bond, should I make a carbocation here or should I make it here? Wherever the carbocation will form, OH minus will attack there. And that carbon becomes the ketone. Here if I make a carbocation, a OCH3 groups is plus M group, which supplies electron to the para position, making it a very good carbocation. So this is the hint. Okay. Tell the answer in the comment box. You will do one more mistake. If you are thinking of this answer, it is wrong. This is right. Tell me why in the comment box. It's from the ether topic. Why D but not C? In the comment box, I need your answer. Homework question number 3, explanation. Why D but not C? D is the answer. Why D but not C? Next one. We want to do this conversion. Alkyne to cis-alkene. This is again an easy question. Lindlar's catalyst will use syn addition. Acetylene is passed through dilute H2SO4 in the presence of mercuric sulfate. Again a PMT question. Just now I told you it gives you acetaldehyde. Homework question number 4. Tell me in the comment box, what would be the best reagent to distinguish compound 3? This one. A but-1-ine distinguished from but-2-ine. Can I use bromine CCl? For answer is no. Everyone will react here. Means this also will react, this also will react. And 3 also will react. Can I use bromine in acetic acid? Can I use alkaline KMNO4? Bayer's reagent. Can I use Bayer's reagent? Or ammoniacal AgNO3. When you go to NCERT, if you see the acidic nature of terminal alkynes, this is one extra reaction that alkynes have. Alkynes which are terminal, this is not a homework question, I just tell you here. Alkynes which are terminal, they carry a hydrogen which is an acidic hydrogen. This hydrogen is attached to sp carbon, which is highly electronegative. So these alkynes can replace their hydrogen with different things. Like if I reacted with ammoniacal AgNO3, which is nothing but Toland's reagent, Ag plus replaces the H plus, giving you a gray-white precipitate. Silver propionide in this case. So yes, ammoniacal AgNO3 can distinguish. This is a good reaction. NaNH2 could distinguish. You will get a bad smelling gas, ammonia. So here what happens is this amide group takes away the H plus, giving you ammonia gas. This could be used to distinguish. Sodium can distinguish. Any acidic group reacts with active metal to give you salt plus hydrogen gas. So popping sound can come, cracking sound can come. Or you can also use ammoniacal cuprous chloride. Ammoniacal cuprous chloride, a red precipitate you will get here. Cuprous propionide, which is a red precipitate. This is not in the NCERT, but other reactions are there. So kindly take care of this. Okay, this is the one. Coming to next, in the reaction with HCl, an alkene reacts with according to Markovnikov rule to give you this product. Again, a homework question. You need to tell me yourself. Homework question number 4. One by one, keep answering in the comment box. What will be the answer for this one? This is also just done by, I've just told you, trans hexene we have to prepare from hexine. Trans means sodium liquid ammonia, where I don't see any option here, which is first option. Lithium liquid ammonia can also be used here. So you need a S block element with ammonia. Same mechanism will happen. Okay, Birch reduction. Okay, again a homework question. Quickly tell me the answer. Homework question number 5. I've just discussed all these concepts. Nothing new. I've just discussed how to distinguish between 1-butyne and 2-butyne. Yourself you need to answer in the comment box. Quickly answer, all of you. And this is the last one. Question number 6. Consider the above reaction. Total number of stereoisomers possible for product P. Okay. Bromine, when it adds here, they are not asking that how many products are formed or what is the nature of product and all. If bromination is done, I'll get a dibromobutane. It's a butene. Here a bromine will come. Here a bromine will come. Correct. Question is not product is a racemic mixture or a meso compound. That is a different type of question which is asked from the stereochemistry. Here the question is how many possible stereoisomers are there for the product. This is the product. As I can see, this product has 2 chiral carbons. How many chiral carbons? 2. But I see it is a symmetrical compound. A symmetrical compound with 2 chiral carbons. You can use the formula here, or I'll just draw it for you. If the 2 bromines are opposite side like this, it is optically active. Then its mirror image will also be optically active. So these are the 2 products I can get. These are 2 different products. If one is dextro, one will be levo. Which is dextro, which is levo, we don't know. You can call them by RR and SS if you want. You can check the configuration here. If it is RR, this would automatically be SS. Third one will be if both the bromines are same side. Like this. then in that case, this is the optically inactive product. So we'll call it a meso compound. Do not draw a mirror image of it. It's a single product, meso compound. So answer is 3 products are possible here. I mean, 3 stereoisomers are there for the final product. Formula is, whenever the symmetrical compound is there, total number of isomers 2 to the power n minus 1, n is the chiral carbon, plus 2 ki power n by 2 minus 1. So when I put 2 power 2 minus 1 plus 2 power 2 by 2 minus 1, which is 2 plus 1, 3. This will be active, this will be inactive. Okay, so a nice question here as well. And the last final thing about alkene-alkyne is the ozonolysis reaction. Okay, whenever you take any alkene and you want to break it into fragments of aldehydes and ketones, just do ozonolysis, react it with ozone followed by hydrolysis with zinc. Finally, what we do is just break the C double bond C, give 1 double bond O here, 1 double bond O here, 1 oxygen to zinc. So 3 oxygens of the ozone are equally divided to this sp2 carbon, to this sp2 carbon, and to the zinc. Finally, we get 2 moles of aldehyde ketones, 1 mole of zinc as the final product. Okay. So in this case, if I break it, 1 double bond O here, we get a CH3CHO, which is aldehyde, and CH2O, which is methanol. Here also, I'll break it, 1 O here, 1 O here. So I get a acetone and a methanol. Ozonide is the, intermediate here, which you can see here, looks like a hut. How the ozonide is formed is not there in your syllabus. Just you can see how the ozonide looks like. Break the 2 bonds and make a hut here with 3 oxygens like this. What are the other ways of oxidation? Other ways of oxidation is with dilute KMnO4, Bayer's reagent, or with concentrated acidified KMnO4, which is not called as Bayer's reagent. It's a very strong oxidizing agent. So when you take KMnO4 in dilute and alkaline and cold form, you get vicinal diols. Break one of the double bond, put 1 OH here, 1 OH here. It has a cyclic mechanism. Cycle will attach from one side. So it is a syn addition. Okay, it is a syn addition. You can remember the 2 OH attack from the same side. Addition of Br2 was anti. Here the addition of 2 OH groups is syn addition. It's a cyclic mechanism. Okay, like this. We get ethylene glycol. In this case, we get propane diol. Okay. Use for test of unsaturation. Alkynes will give this test. Alkenes will give this test. Alkynes will not give a vicinal diol. They will give a vicinal dicarbonyl compounds. Okay. So if I take a ethyne, for example, in ethyne, you get finally, instead of getting a ethylene glycol, you get a glyoxal. When you take a ethyne, or when you take any alkyne, R, C triple bond C, R. First time OH will attack here, second time OH will attack here, giving you 2 OH on the same carbon. And we know that 2 OH on the same carbons are never stable. So they easily lose water like this, easily lose water like this, finally converts to vicinal di ketones or aldehydes like this. Okay, still used as a test for unsaturation. The pink color of KMnO4 decolorize in unsaturated compound. Benzene never react like this. So benzene will not give you the Bayer's reagent test. But when you take a concentrated hot acidified KMnO4, in that case, reaction will be taking place with more vigorous oxidation. It will break all the 2 bonds and oxidize the 2 sides alkyl group to either aldehyde, either ketones or carboxylic acid or CO2. You can see here carefully. So just remember, whenever your doubly bonded carbon carries 2 hydrogen, it will become CO2. When the doubly bonded carbon carries one hydrogen and one alkyl group, that carbon become carboxylic acid, RCOOH. And if a carbon carries no hydrogen but only alkyl, then it will become a ketone on oxidation. Okay, so three things can happen. Ketone can happen if the carbon carries zero hydrogen. Carboxylic acid can happen when carbon carries one hydrogen. CO2 can happen if carbon carries two hydrogen. Okay, looking at this, for example, here if I see this carbon carries two hydrogen, it becomes CO2. This carbon carries zero hydrogen, it becomes ketone. This carbon carry one hydrogen, carboxylic acid. This also carry one hydrogen, carboxylic acid. So you can break the carbon double bond carbon, make the fragments of organic molecules. Okay, this is the one. So these are few more homework questions I am giving you here. I will keep the class up to here as the time you have the time for the next particular class now after this. So I hope you all have enjoyed the class, and few homework questions I am showing you here. And we'll continue more with in the next class, where we talk about alkyl halides, little bit of benzene, and the next topic, right? It's a homework question for you. Write down the answer in the comment box for the homework question 5, 6, homework question 7, and this one is 8. So total 8 questions I am giving you as your self work. These are all the things we have discussed in the class today, and that is all for this class. I hope all of you have gained some knowledge, some extra knowledge, and revised all your concepts quickly in this 1 hour. Your hydrocarbon chapter is almost complete. Just the methods of preparation of benzene is remaining, which is not nothing special. Aromatization you have seen, there is cyclic polymerization of ethyne, which is extra. Rest of the reactions will keep coming in the next following chapters. So that's all for this class. All the very best for your RE-NEET exam. I hope you will study much better in the next 32 days that you have, and crack it with the even better marks and go to an even better college. It's not a setback for you. Okay, it might feel like a setback for you, but I want you to take it as a challenge and make your best comeback of your life this time. Okay, so I hope you have enjoyed the class. Thank you very much. You can like the video if you have enjoyed the class. Tune back again at the same time tomorrow as well. Chalo, bye bye. See you all in the next class.